Okay, I will start this. So let me see. So what I am supposed to do now today is to explain you about another symmetry. So far what we have said, let me explain. That is about symmetries beyond space-time. Symmetries beyond space-time. I said one is that is gauge symmetry. I called it as U1 gauge symmetry. Okay, and then 2. I don't know. This leads to conservation of charge. Charge conservation follows because of some gauge symmetry. And I don't know a name for this, but I will say there is a conservation of baryon number. That has to be a continuous symmetry. So we said that is some symmetry which we don't know yet. So that is one more thing that I told you. And third, conservation of lepton number in different sectors, in different generations. We don't know how to write this, but in different generations, you have lepton number conservation. So with that, now I am going to tell you about another gauge symmetry, some gauge symmetry which we don't know. I will call this as isospin symmetry and explain it, and associated identifications. That is, we don't know anything. We are trying to identify a few things. So that is to know about particles. It is possible whether it changes color or it changes it fumes or anything. We have to learn some different symmetries and the associated conservation laws. After that, I will be able to say that certain things, and then we go ahead to talk about our classifications. That's what is the whole idea. Okay. So let me say we have let me say isospin conservation. So in that, I'm just explaining it to you shortly. So we had Heisenberg had just thought that it is neutron is almost identical to the proton. That is, if you have compare masses of proton and neutron, they are almost identical. It is 938 and 939. In the suns are strong interactions. This 2 MeV or 1 MeV difference is negligible. So we say neutron and proton are almost identical. So I will start saying that they may be same. And neutron proton and proton proton interaction are identical. That is, what I am trying to say here is you might have learned it in your general class, but I cannot do an experiment like that. But suppose I have one neutron and another neutron, I want to check what is this strong interaction. Suppose I want to say what is strong interaction here, and N and P, what is the strong interaction associated with this? What is strong interaction or nuclear interaction? And I want to see proton is negligible when you think about strong interaction. You have to know which is stronger, which is light, weaker. So compared to Coulomb interaction, strong interaction dominates. So it is noticed by people that all these are same. That is, if I only focus on strong interaction and I have a measurement instrument, suppose I have a measurement instrument to check on proton and neutron, they are all identical is what we notice. So this is noticed by Heisenberg. Don't ask me how they noticed it. That's deep on what I am saying. So because of this feature, that is, one is two particles, proton and neutron, they have identical mass. Only thing that is a difference between neutron and proton, it looks like, is that neutron is neutral, proton look at only in electromagnetic interactions. Suppose I ignore charge and look at what is strong interaction. As you know, strong interaction does not bother. Neutron also have a strong interaction. So we should remember that nuclear interaction, which binds neutrons and protons together, does not depend on charge. Coulomb interaction does. Electromagnetic interaction has a feature that it depends on charges, but strong interaction does not depend on charges. So then I will ask, why these two are identical. If I neutron and proton may not be seen as different if I view it from the point of view of strong interactions. That is, if I look at it from electromagnetic interactions, neutron and proton are different. But analogy, what I want to tell you is, certain things. That is, suppose I have an electron. This is analogy, an example, to make you understand the concept of isospin. What I am trying to say is neutron and proton, that is, they are not different as far as strong interactions are concerned, is what I am proposing. In order to highlight that they are same, there's under strong interactions. Let us say hydrogen atom or some atom, if I take it and it is in a energy level, say hydrogen atom, suppose it is in a energy level and there are two electrons can occupy this energy level because spin up and any energy level in hydrogen atom or any atomic level. I hope you agree with me because spin up is one chair available, spin down is another chair available. That same energy is same, but two particles, one with spin up, one with spin down can occupy. That is what you used to call as degeneracy of a given energy level. My interest is not to make, but what I want to tell you is, this is an electron with spin up, this is an electron spin down. Now, if it is occupying same energy, I don't know which is spin up, which is spin down. I cannot call electron with spin up as some electron. Nobody called it like electron and pelectron. No, we don't call it like that. We say it's an electron with spin up. Spin is a degree of freedom for an electron. It comes with 2 degrees of freedom. One is up, one is down. But now imagine that I have strong, suppose I apply a electron is in one of the energy levels. One is up, one is down. Let me apply a magnetic field. In the presence of a magnetic field, you do know that I'm giving you analogy. This is not for my particle physics class. I'm trying to make you recall about certain features that you have already heard, which is to be technically a magnetic field. I do see that this is treated as a perturbation. That is, in theoretically, you treat it as a perturbation. Under a magnetic field, 2 different energy levels will be. Energy levels get here, electron with spin down has gone up. That is, under a perturbation, you will be able to see electrons as 2 different energy levels. Each energy level carries 1 electron, whether it is spin up or spin down. So otherwise, I would have called it as same electron, no change. It is only an electron. I did not give 2 different names to our electron. Now come back. If I did not have, if I had only strong interaction, I would have treated as same particle. I will call the same particle, give it a name like an electron with neutron and proton as nucleon. From now on, I call it nucleon, and nucleon with isospin up is what I will say. Isospin up is proton and isospin down is neutron. I will just make a hypothesis. This was done by Heisenberg. Now I will again tell you, a nuclear look at strong interactions. Only strong interactions I am taking. The nucleon is the same. It doesn't look like a neutron and proton. I cannot distinguish it. It is somewhere here and turn it around by 90 degrees. So it becomes another square, same square. You will not say which is the square earlier, which is the square later. You will say all are same. So I will say and proton. That is like saying I kept a neutron and I see what is the strong interaction of a neutron. Check strong interaction of a neutron. And then replace a neutron by a proton cannot be distinguished. So I will say it is like a square which is turned by 90 degrees. Neutron and proton appear to have some unknown symmetry, which I am going to call it as isospin. I will tell you in a minute. So that is what is the agenda today. So I said Heisenberg proposed that neutron and proton are 2 different states of the same particle. To have one single particle with multiple degrees of freedom. That will be very ideal, nice. So Heisenberg wanted to club neutron and proton and say that they are same particles. There are 2 different states, like particle called as nucleon. I denote it by capital N. Nucleon is denoted by capital N. That is a particle for me. And then I will say that denote neutron and proton isospin states. I will quantum state for isospin. I will write proton a ket. Remember, any particle is described by its quantum state. Quantum wave function. Wave function is a loose language. We will say a quantum. I will say it is nothing but isospin up. And neutron is isospin down. I'm introducing this. Heisenberg is hypothesizing this concept because as far electron and proton are same, so it reminds me of electron spin up and electron spin down. So proton and neutron are isospin up and isospin down. Then come back here. What I will say is, 1 minute, what I can say, only strong interactions present in this world. I only have a strong interaction present. Then neutron and proton, I would have called this as nucleon. both have same masses, no distinguishing. So it is only a single particle, neutron, nomenclature. Then I see that there is a perturbation, which is electromagnetic interaction. Nature splits neutron state and a proton state. This is isospin up, which is up, which is down. We will see. Neutron has isospin down, up and down. So I will denote this as proton as isospin up. This is isospin, not spin. Spin is something else. Electron has spin, but neutron, now I will say they are isospin half particles with the isospin value up and down. Why half? I will tell you. I have to develop mathematics for it. I will say they are similar to spin up and half particle, but spin is different, isospin is different, because spin is known to you in atomic physics, but what I am talking about is strong interactions called as isospin symmetry. Neutron and proton are not distinguishable as long as only strong interactions are there. But as long as electromagnetic neutron is different, that means it is like nature switches on its own magnetic field like interaction. Magnetic field is created in a lab. You can switch on a magnetic field and see levels get split, that you can see. But neutron and proton are seen as two different particles for us because nature has switched on electromagnetic interactions. If I could have switched on and neutron as same particle, I need not have given them two different names, is what Heisenberg argues. So this mathematics of isospin is exactly similar to spin. Spin has a mathematics posed by Heisenberg. He introduced the notion of isospin in an analogous manner as spin. That means, how do you introduce spin in your quantum mechanics class? You will say a spin has three y, j, z. Three sets of three operators. You call them as spin operators or angular momentum operators. That is how you start mathematics of angular momentum, or may have to get crystallized that, okay, spin half is associated with our electron, proton, neutron, etc., etc. So I do get mathematics first and allowed values are seen. That's how we go ahead. So what are the properties of these spin operators? I will say Jx, Jy is equal to I into Jz. I will not write a H bar because H bar, it can be any operators obeying this kind of a relation. Quantum mechanics or mathematics does not know what is a physical feature of a system. It doesn't know whether I am doing nuclear, that is words. So Jx, Jy is Ijz. What is Jy, Jz? That is going to be Ijx with a minus Yz is Ijx and so on. So then we would have said, fine, I have all this. J squared commutes with Jx, Jy, Jz. It's a common eigenstates of J squared and Jz. This is operators J squared, Jz. Common eigenvalues are J and M. And what are the allowed values of J? J can assume 0, half. This is a commutation relation. I arrive after mathematics. I get a result that is completely mathematical result, but I do see 0, half, 1, 3 by 2 kind. The mathematics leads to identification that I have 0 spin, I have half spin, I have 1 spin, etc. So that is what is the theory of angular momentum. Who tells you that you should not use something same as commutation relationships? Isospin. Isospin is also a set of three operators, but nothing to do with XYZ. I will say it is I1, I2, I3, and they are operators. Imagine things. This is mathematics where I say it is similar to angular momentum algebra. I will say I1 commutator I2. If you write a commutator, this is momentum. Only thing is that I have changed notation to make sure that you understand it is not spin. It is different. Give it a name. Heisenberg prefers to give it a name called as isospin. Then I will take, suppose I squared, I define it as I1 squared plus I2 squared plus I3 squared, square of angular momentum operator, and I3, they together of these operators, no physics, only mathematics, they will give you, I write the states as I without hat and I3. What are the allowed values of I? This is some state. So I get some simultaneous eigenstates using same formalism as spin, but the concept is different. Physical concept is different. Neutron and proton fit in here. It's nothing to do with spin also. This is something different. So I will say isospin assumes values 0, half, 1, 3 by 2. Why? Because it is the same commutation relationships. It leads you to the allowed values of the observable. That is, whatever is the observable can take the values. If Angular momentum gives you 0, half, 1, 3/2 as possible values. Isospin also has same possible values. If I obeying same commutation relationship like spin. So now I again want to emphasize giving an analogy, not this. Suppose I say you have an equation d squared f by dx some omega squared x. This is the equation. You want to find out, okay, sorry, I will say f of x. This is what is one equation. And I write d squared g of x by dx squared is equal to omega squared g of x. Do you say that they are different? Do you say they are different or same? Write it in chat box because I can't hear you. Message me. Do you say given different looking equations, different looking notations are used, results are the same or are they different? I want your answer in chat box. Okay, one answer I got. Nobody else is answering. I want some answers. Without interacting, I can't do your class. Only one answer. Okay. All right. At least 4 of them are decent enough to at least interact with me. Thank you to them. And others, please, it's not. So it's only an analogy. With that analogy, I am going to say, fine, this has same equations. Similarly, I will say, if you use this kind of a commutation relationship with, so now I come back to my slides, call something as isospin operator. This is a set of 3 operators, just like angular momentum operators. You have learned angular momentum called as isospin operator in your context. I am introducing to you something similar to commutation relationships, but physics-wise different notions. That is called isospin. So I will say relationships. You don't have to worry. It is same angular momentum relation without a h bar. H bar stands for angular momentum. Isospin has no units. I don't give it any units. It's on are same. So then I will say, I can define isospin eigenstates. My notation is to write eigenstates of isospin as capital I3 without hat. Hat denotes the eigenvalues I, minus I is less than I3, less than I. Like how J and M. M varies from minus J to plus J. I3 varies from minus I to plus I. So eigenvalues I of squared, I2 squared and I3 squared. And third component of isospin operator I3. So we obtain, if I use the same concept, we obtain I squared acting on I3 is squared acting on Jm is J into J plus 1 into H bar squared Jm. Same things that I'm using. Then I have various relations. I plus takes I3 to I3 plus or minus 1. Like how ladder of another state, I plus or minus 1 shifts I3 to I3 plus or minus 1. So I plus or minus 1 are ladder operators like your J plus J minus. So there is a I3 and ladder operators. So that's what I need you to know. And then I will say, fine, with that concept, I am coming to strong interactions now. This is the mathematics required for hadrons, which are strongly interacting particles, come with their isospin value I. They are grouped into 2i plus 1 isospin multiplets. Why 2i plus 1? I will now ask you. Suppose I give you what exercise, which is algebra. So I will ask you, if I is equal to 0, what is I3? I want your answer. Answer I3 is equal to what? So you have to send me chat messages. What is I3? If I is 0, what is I3? All right. So 2 of them have quickly answered. For my earlier question, 2 equations with 2 different functions, but the same equations, they have same. Please correct yourself. My question had one answer and the answer was same. Solutions are same. Now, when I am asking you, I is equal to 0, I3 is also 0. Now I will ask you if I is equal to, again chat, allowed values of I3. So I do see that there is confusion. I3 is like, if I write a J and M, J is equal to half. What are the values of M? So please send me chat messages again. J is half. What is M value allowed? I am checking chat messages which come from now on. J is half. What are the allowed values of M? I'm waiting for your answer. Okay. So I got only one answer. Other momentum theory is not known. Particle physics will be zero. Nothing can be known. Angular momentum, I don't want your derivations. I want your concepts. So if angular momentum J is half, M is plus. This is a Hilbert space. I call that as a small space with the dimension 2J plus 1. That is number of states, basis states tell you what is the dimension of your J. You have two states. So I will say if J is equal to half, 2 into half plus 1 is 2. So if I say this, and then I wanted to tell you that for any angular momentum J, there are basis states for M value going from minus J to plus J is 2J plus 1. That is the count that you have learned in your angular momentum theory. If not, write a copybook and make sure that you understand equal to 1, write M value and see if it fits this 2J plus 1 formula for number of states. Number of states means that's all that you can have. No more, no less for angular momentum. That tells momentum can be expanded in terms of these basis states. So we say this is a complete set of orthonormal basis states, mathematics wise. They define the dimension of angular dimension. That is how many states are there, tells you the Hilbert space dimension. That is a word used. So now I will say I is equal to half. I told you result of I3 is same as I3 is now. Now you tell me again, because I got a wrong answer, I am asking you again. So somebody is saying 0 plus half minus half. I don't know why 0 plus half minus half. Angular momentum never gives you with J. So if angular momentum J is equal to half, M can only be plus half minus half. It varies from minus J to plus J. Suppose I have J is equal to, I will write again. This concept has to be clear. I say J is equal to half. This is M is equal to minus half. Then I add to plus half. So I say for J is equal to half, M takes values minus half and minus half plus 1. That is in steps of 1, it increases. Steps of 1. So that gives you the allowed value. So if I say J is equal to 1, M takes values from minus J, that is minus 1, to plus 1. That is minus 1 to minus J minus 1. The same value I write, plus add it to plus 1. So I get a 0. Then next 0 plus this, write this here and add 1. So that is plus 1. You have already reached the highest steps of 1. That is what you should have learned in your angular momentum. Please record it and then you have to answer according to the rule. So now I will only say if you have answered that, that means your angular momentum is very poor. Please learn only the results, not derivations. At least for my class, I need results of angular momentum. So if I is equal to half, I means I squared plus I3 squared is an operator. It has eigenvalues I into I plus 1. And if I is equal to half, I3 takes values from minus I to plus I in terms 1, another value. Minus I plus 2, another value. Where? Up to where? It should become plus I. Till then, I keep varying. Now, if I is equal to half, I should write I3 is equal to minus I. What I write? One value. Next value is minus I is minus half. Fine. I have to write. This is a combination of. Then I should write minus I plus 1. What is that? That is minus half plus. That is going to be plus half or minus half. At least now you should answer. What is 1 minus half? What should I write here? I don't want to insult you. This is half. You are mixing your concepts of physics and mathematics. When I ask a question which is 1 minus half, don't bring in isospin, don't bring in electron spin, nothing. It is so now. If I say this, where is 0 coming in? It doesn't come. When you say angular momentum also, M varies from minus J to plus J in steps of 1 is a result that is result, whatever I am telling you now. So I will go back and explain it to you. When this is all results that I have written. I am going to say hadrons, that is strongly interacting particles, come with symmetry. So isospin I is good value for baryons. That is, if I say that isospin is conserved quantity or constant, its eigenvalues should be used for labeling quantum mechanics. Something is conserved. It means, it doesn't mean that for all times it remains the same, like in classical mechanics. Angular momentum conserved means value of angular momentum remains the same in classical. Spin squared eigenvalue, that is going to be denoted by I, and that is for one particle, one hadron, you do have one isospin. Then there are different substates like M is minus J2 plus minus I plus 2, etc. up to I. Note that the action of isospin ladder operates. That is, if you take I plus or minus 1, its job, I am telling you that from the transforms the isospin state I3 to another isospin state I3 plus or minus 1. It is shifting I3 to I3 plus or minus 1. So with that mathematics that nucleon is an eigenstate of isospin. Nucleon is a particle. A quantum particle has a state. Which state? I will say as long as strong interaction eigenstates. All other things that are different, but isospin is defined only for a strongly interacting particle. And I say isospin, eigenstate of isospin, when I get third component of isospin has eigenvalues minus half and plus half. So I will say I3 is equal to half corresponds to a particle proton. This is my theory. Isospin emerges naturally because I do see in nature identical particles, proton and neutron. As far as strong interaction is concerned, it is the same. What is the method theory of isospin? Which is same as angular momentum, but the concept is different. Neutron and proton are same, and it is like electron spin up, electron spin down. Neutron is a spin down nucleon, and isospin down nucleon, and proton from now onwards, as long as strong interaction is concerned, proton is a isospin half, I value half, I3 is plus half. Neutron is same I value, I is equal to half. There are two states, not more than two. You don't have n nucleons, only two nucleons. There is nothing called as three nucleons. There is no isospin zero nucleon. Only isospin up nucleon, it is proton. Isospin down nucleon is neutron. So I will say proton can get converted into a neutron and vice versa under the action of nature. Nature has strong interaction which changes a neutron into a proton. So strong interaction can convert a neutron into a proton by conserving the value I. I doesn't change. I with 3/2 can. So it is like spin. I am just stating it in English. Isospin proton can get converted into a neutron, but isospin value, capital I, that is preserved. So I will say that if you are confused, you have known language. So then I will say, remember, pions have three different states. What are pions? I had introduced it. So there are three pions. They are mesons. So mesons known to you, there are pi minus, pi 0, and pi plus. So these are called pions. So there are three different charge states. They all have same mass. And as far as isospin is, that is strong interaction is concerned, they interact the same way. That is the only reason why I say that spin 1 particles, because I3 value can assume when isospin I is equal to 1, I3 will take values 1, 0, minus 1. So I will say pi plus is minus 1. Which is plus 1, which is minus 1 is a convention. I choose to write highest charge particle. Pi plus is a highest charge particle in the group. So pi plus, that is my convention. Charge, isospin, are they to do same? Are they related to each other? I'm not saying that. I'm only telling you a convention. With the convention, I write what is a pion. I'm introducing you in the strong interaction called as isospin. Now I am giving you what is isospin, mathematical theory of isospin without deriving mathematical results, because you already know the mathematics of angular momentum. I don't need to remember the results. So from that, I am going to conclude that neutron and proton are called one single nucleon. And pi plus, pi 0, pi minus are nothing but one single pion. Pion comes with an isospin value minus 1. The one with isospin value 1 is what is called by us as pi plus. Isospin third component 0 is what is called as neutral pion by us, and isospin. But all are pions according to the hypothesis that I am telling you. So pions are interconvertible again under the action of isospin ladder apparatus. Any I is equal to some value fixed, different. They cannot go to from that sector to another sector. So with that, I will only say, what is the statement of symmetry now? I will say strong interactions are invariant under rotations. In the very funny notion, you have to mix your visual representation with the abstract representation. What is visual to you? If I say XYZ axis, X, Y, Z, this is our space. In space, the coordinate system. How do you rotate? You will say Y goes to Y prime, Z goes to say Z prime, and X goes to say X prime. This is a new coordinate system, X prime, Y prime, Z prime. Under such a rotation, we say under rotation, If laws are remaining invariant, we say isotropy of space. That means laws of physics are invariant under spatial rotations is what we say. I hope you follow what I said. Space-time symmetries are giving you a mental picture of what is a rotation. Then I uses a XYZ coordinate system. Another observer uses a X prime, Y prime, Z prime coordinate system. Both should have same laws of physics. Laws of physics do not depend on whether my coordinates the way physics laws should be is the philosophy. So this is understood by you when I say there is a mathematics behind it. And I said space is isotropic, has a conservation law. And I said angular momentum is conserved. That is this something called as operators I1, I2, I3 and call that space. That's not a XYZ space. I call something as isospin space. What is a isospin space? There is a operator states are there, I and I3. These states are interconvertible into one another. I3 goes to I3 plus or minus 1, etc. Like how we write X prime is X relation that we write under rotations. We will say I3 get mixed up with I3, something like cos theta into I3 plus sin theta into I3 plus 1, like such a relation. Linear combination of isospin space, rotation in the isospin space. So here it is rotation in the actual space. I can identify that there is some rotation in the isospin space. What is conserved in space? Say, if you have a rotation in isospin space, conserved quantity is isospin I value. So particles belonging to a given isospin I with different I3 values are I is the statement of conservation of angular momentum. This statement, I repeat, I read, strong interactions are invariant under rotations in the isospin space. Space-time isospin symmetry cannot be seen by you, like how I am saying, keep a neutron and check strong interactions. You cannot see it, but keep a proton, check what is strong interaction. You cannot, I call that as isospin symmetry because the mathematics is same as that of angular momentum. I assume that there should be some hypothetical rotation called as rotation in the isospin space. Rotation in isospin space gives me conservation of isospin. That means particles belonging to a given isospin I, they are all identical. They are all same. I names. If you did a mistake of giving it a name, only recognize the particles with I3 values. Don't do anything else. I is the figure of merit for you from now onwards as far as strong interaction is concerned. So this is a process A plus B going to C plus D involving strongly interacting particles, hadrons, total isospin quantum number I and the value of third component I3 should match on both sides. That is a side isospin. I will say it is isospin of particle A, isospin of particle B. But addition is like angular momentum. Every mathematical rule is like that from IA minus IB to IA plus IB. Please don't get confused with JM. M varies from minus J to plus J. If I say two J1, J2 are combined to give you a total J, that is a different rule. Remember, angular momentum has some important concepts. Now I am telling you about addition of angular momentum. Earlier, while classifying particles according to isospin, I was only talking about isospin eigenstates. Now I am talking a simple addition. It's like angular momentum addition. That's all I want you to know. This should match. So RHS isospin spin, that is IC plus ID, should match with left-hand side isospin. Process may happen. Otherwise, isospin symmetry prevents a process, strong interaction process, to occur in nature, is what we say. It is complicated, but you have to see it. So you have to learn it. That's very important. Beyond space-time symmetry, you have to learn by knowing the algebra, nothing else. Learn the algebra for known particles. Only by writing and rewriting and thinking, you will get it. Nothing else will help you. So I3, left-hand side, but I value, total isospin, it has to be added like how you add angular momentum. With that, I will say that, I give an example. For example, if I take a strong interaction process, proton plus pi z, write it for your understanding. Proton plus, what did I say there? Proton plus pi 0 goes to a neutron plus a pi plus. Tell me the isospin values of left-hand side, I and I pi 0. I want to know that. And I3 proton, I3 pi 0. I will ask a name. You have to answer me in this, what is the value of it in chat box. So what is the I of P? Proton isospin value. What is this proton isospin value? Let me choose a name. Akshaya. What is I of P? Send me a message. Okay, isospin for proton is half. Fine. What is the I3 value of proton? Akshaya again. I3, third component of isospin. Akshaya. Proton. I am writing for proton. Proton has only one value of third component, isospin. It's not two values. Third component of isospin of a proton. Then I will ask you about neutron. First tell me about only proton. All right, it is half. So I will write it and continue. The proton is half. I3, third component of proton is also half. Now I will ask pion. What is the pion isospin? Isospin is different. Third component of isospin is different. So what is I pi 0? At least tell me I pi 0. Okay, Kirtana is already telling me it is 1. Fine, good. And third component of isospin, Amruta. Third component of isospin. This is 1. Fine. Third component of isospin. I will check if anybody has answered. Okay, very good. 0. So this is, you are getting into it. Now, if I say proton plus pi language, a child doesn't know to start, say Ra, it will say La. So I will say Ra, instead of Ra, a child will say La. Proton, pion, neutron, pi plus are all child language, but an isospin language, 0, I3 pi 0, like that I have to say now. So this is today's learning. From being a child, you are growing into an adult. So I will now say, what is left-hand side I value, LHS, isospin value for IP is equal to half and I pi 0 is equal to 1, half plus 1. What are the allowed values of angular momentum addition if you take half and 1? To do this, say half plus 1 according to what you have here. What are the allowed values? Somebody is saying this. Somebody is saying 3 by 2. I don't agree with only 3 by 2. There is one more value. You have to tell me one more value. Angular momentum addition is not repeating so that you copy it to yourself. Angular momentum addition is not only one value. Half plus 1 is 3 by 2. No, not just that. It has something else also. Minus half. I value I is always positive. Please remember that. I3 can be negative. Minus I2 plus I. So you need to write these things down. And now tell me what's that. So I will say half plus 1 is half and 3 by 2. So with that, I will say that is what is isospin left-hand side. What is L right-hand side? Isospin value right-hand side. Neutron is half, but I neutron is half. And I pi plus is 1. I3 pi plus. What is I3 pi plus? Please tell me. I3 of right-hand side particle pi plus. Okay, good. Plus 1. So I write plus 1, right? That is again half plus 1 because neutron is there. Third component of that is pi plus is there. Left hand side is different particles according to our childish language. Right hand side is also different, is going to be half and 3 by 2. This is allowed as far as RHS is isospin is concerned. So then I will ask, what is third component of isospin? That is also to be matched. So left side is proton, that is P, and pi 0, that is 0, and I3 right hand side. So I have in right hand side, I have a neutron. Neutron is minus half and pi plus, that is half. Add them. I3 addition is simple addition. I'm telling you because angular momentum also follows the same rules. I cannot teach you angular momentum. I'm only repeating you. By doing it repeatedly, you will learn. What is left hand side I3 LHS? Half plus 0 is half. Right hand I plus has a 1 value. I wrote it wrong. 1 minus half is plus half. So both are same. So this process, proton plus pi plus, no, what is that I wrote? Proton plus pi 0 goes to a neutron plus pi plus occurs in action. So similarly, we can check varieties of things. Oh, what did I write here? Oh, this is a pi minus. What is the mistake that I did? I wrote a pi plus. If you write a pi minus here, this is pi minus. What is the isospin value on right hand? Minus 1. That is minus 3 by 2. So it does not happen. If I write P plus pi 0 going to N plus pi minus, I3 LHS is equal to, sorry, ILHS is equal to IRHS, but to I3 RHS. So if we don't get confused, this process does not happen. Even according to charge conservation, it does not happen. But my training today is about isospin. So focus on isospin. Isospin symmetry is not a space-time symmetry, but it is an internal symmetry obeyed by strong interactions. With that, I will not continue. I will tell you about it in the next class because it is difficult to understand particle physics. What you need to know is the results of angular momentum. and work on the whatever is given. So I will explain it in the next class.